泪，寒风刺骨吹，那也比不上你给我的伤悲。我承受着最黑，要装作无所谓，我是冬天里可怜的白玫瑰。那么黑，月亮与我睡，也不应该让我一个人醉。寂寞的滋味，让我一个人体会。我是冬天里孤单的白玫瑰。就算大雪飞，就算寒风刺骨吹，就算你给我再痛再苦的伤悲，我不会落泪，也不会继续憔悴。我是冬天里坚强的白玫瑰。
To get a scene CSV of FANUC 710 6X Loba. In front of the screen you can see FANUC 710, the big Loba, which comes from Century Company, was President Wei. The file is emailed the day before yesterday. Since we are waiting for the music, we postponed for 1 day until published on YouTube. Whenever we get the SGS file, we have to go into SolidWorks and open the old file to find the right folder, the FANUC 710, and translate the coming IGS file. This is coming IGS file, and translate it into SolidWorks inside geometry file. Open it. The coming IGS file will translate through several processes until the 3D geometry model displayed on the screen, which is the assembly file of the Loba. Before doing anything, we have to survey if the Loba is located correctly. Let's see. This is x-axis, this is y-axis. So the Loba stand up, the sky at the top. So it is correct. And then we survey the original of the Loba. We put the cursor, press nothing. Then the center of the Loba, the original point of the Loba will display at these points. This side cannot see correctly. Then we change to the up base position, and then see the original points at the bottom of the foundation. So this Loba is correct. Stand up and in the right position. And the home position is just like this. This is X positive. The Loba point to X positive. And the component 3, this joint and this joint, the X coordinate should be the same. That means this bar should be vertical. This is very foundation, very standard 6X Loba. The 6X Loba definition, the first axis is always rotate around the z positive direction. The second join rotating around y-axis coordinate. The third join rotating around y positive as well. The fourth join rotating around x positive direction. The fifth rotating around y positive as well. The sixth rotating around x axis. This sixth basic rotating direction is standard definition. After the transformation from IGS into the geometry displayed on the screen, then we have to save the assembly first by means of a save file. Give the style as ASM, the name the same as before IGS file, and save it. After save, we survey the SY-Z coordinate is correctly located. Then we have to survey the separation for each J1 to J6 component before doing any combination. Suppose for the base starting from the foundation. The foundation, you pick here, it will reflect here. And then we press here, it will reflect the total geometry on the screen. You can see this one and this one. This one is transform 1, 2. This one is the transport 2. Because this is a really big loba, this 2 stem is better for the workers stand on. Therefore, the basement not only this component, the transport 1 and the transport 2 has to join the foundation, because these two fixed on the basement to form a total foundation. And then we survey the J1 component. The J1 component is okay, single component. The J2 is single component. Quite easy for us to separate the component in individual. And this one, J3 is single component. And how about this one? J4 is single. It's easy to separate the component. And how about the J5? Okay, J5 and J6 combined together. We separate it first, then handle J5, then J6 separately to get the 6, including the basement, totally 7 component, and then to add a tool we have to get a PRT file for this 7 component, and then to get IGS file of this 7 component. Okay, we save the assemble file already. Now continue to separate starting from the basement. Okay, we surveyed already the basement, including the first one and these 2 transport. So we delete this one until here, including the last one. Leave these 3 on the screen. After highlight, how to remove it? Simply by pressing delete key of the keyboard and select the second, delete all. When we're doing the color change, whenever the parts without colors, we change the color. How to change it? Simply by putting the cursor on top of it and press the right key of the button and choose the outlook and pick the white circle, and the color shading area will appear at the right button at this side. Then we can press any position to choose the color. If we want to give the standard white color, we have to change R pixel to 255, G to 255, the blue color pixel to 0. Use RGB representation. Then we make sure the color is okay, and then change this color. Use right button to pick this component and pick outlook and pick the white ball and pick the yellow any place area and correct R pixel to 255, the G pixel to 255, and blue pixel to 0, and make sure. Okay, after these 2 component color changed to yellow, then we finished the definition of foundation. Then we save PRT file and IGS file as well. How to do it? Simply by pressing to choose, save another file, another new file. First the style, choose .prt. The file name we give FANUC. We use the short name FN represent the FANUC. The base according to the naming specification, we use FN0 as foundation. Foundation means this one is fixed on the ground, will not move. FN0. Then we save FN0.prt. After that, we use save another new file to save .igs file. So the style has to be changed into IGES and give the file name FN0. Then we save FN0.igs. So after foundation finished, then we can doing the same way to handle what? Handle the J1. The same, remove the component to leave J1 component on the screen, and then save the J1 as fn1.prt, and then save another new file. The style, choose IGS, and the file name FN1, and then save it. Then we can get FN1. The main purpose is to get the PRT file and the IGS file of each component. The FN2, we can get FN2.prt as well as FN2.IGS. The same, we can get FN3.prt as well as FN3.IGS. We can get FN4 IGS and FN4.prt as well. As to FN5 of FN6, we survey the radius, which is combined together. We have to do one extra procedure to separate this twin component. How to do that? Okay, we continue to demonstrate the way to separate J5 and J6. Before doing anything, we have to remove the display on the screen. How to do it? Choose the file and close the old file. Save nothing. And to clear the screen. And then we open the assembly file. You can see the picture at the right side. Before choosing it. Okay, it's correct assembly picture. Then we press the left button of the mouse to display on the screen the assembly of the 6X robot FANUC 710. So right now we are talking about the separate the parts. These parts, pick it and press selecting here. You can see the total geometry highlight in here. So we remove the rest, leave this one on the screen. How to do it? Put the mouse on first of it and press the left key of the button and move the cursor to first and press the left button of the mouse together with the shift key of the keyboard. The rest three, pick one by one by pressing the control key of the keyboard and together push the left button of the mouse. Pick one by one. Okay, we left this component on the screen. How to remove the highlight parts? Simply by press the delete key of the keyboard and select the second delete all of them to leave this component, the single component on the screen. Before we doing anything, we change the color first by pressing the left button of the mouse and choose Outlook and choose the white ball and pick the yellow parts and give the RR pixel as 255, green pixel as 255, the blue pixel as 0. Make sure. Okay. Then save this component first before separating. Okay, how to save it? Simply choose file, save another file, give this the type .prt. Okay, we want to separate the J5 and the J6. We give a file name outside J1, J0 until J6. Right now, for example, we give the name of this component fn10.prt, save it temporarily. Okay, right now commencing to separate each part. The J6 is dark parts, the rest is J5. So we get the boundary between J5 and J6. The boundary is here. We enlarge it. If there is any gap, even really small gap, we can pull the wheel toward our body to enlarge the gap. You see, large and large, until we can put the cursor on top of it, and then press the left button of the mouse. And then we choose a normal to this surface. It will display a normal of the selected surface. So we can create a square surface on top of that selecting surface. How to do that? We can choose the sketch function. Sketch. Then at sketch 1, open here. Then we can pick the square, the two-corner square. How to round it? Choose the function first. Move the cursor and to the left top button, left top corner, and press the left button of the mouse, and continue pressing the left button of the mouse, and pull the mouse down to the right button corner. Cover every joint on the screen, and then release the left button of the mouse. A surface will be created along the boundary between J5 and J6. So the boundary is created, boundary square surface created. We close the definition. And then how to remove the left part or remove the right part to get J6 or J5. We simply choose assembly function and see which one. Here, to enlarge the function, two functions appeared on the screen. One is tend to remove material. Another is rotating to remove the material. So its translation, we use is tend to remove the material function. After choose it, you can see the system will automatically generate 10 millimeters thickness along the arrow direction. This 10 millimeters still not cover the whole J6 component. So we enlarge 10, suppose to 30 millimeter. Press enter. Then you can see on the drawing this surface, square surface created is 10 to 30 to generate this surface cover the J6. If we remove these parts, then we can get J5 altogether. So we just say sure. The system will automatically remove the J6 for us and to get J5 on screen. We press any left button to put the cursor anywhere to remove the highlight. Then we can save the J5 component save what? Save.prt and save IGES. Then we commence to do that. Save another new file function. The type choose .prt. The file folder FANUC 710. This is component 5. Give the name fn5 and save it. Save fn5.prt first, and then commencing saving the .iges. How to do it? Choose file and save another new file function, and the style give IGES, and the file name give fn5 to save fn5.iges. Save it. Okay, so after file saved, then we have to do to get the single the component 6. So we go back to FN10. We have to clean the screen first. No saving. And then choose the component FN10, which will display on the screen negative. Then how to separate the J6? The same. We found the boundary between J5 and J6. Enlarge the gap until big enough the cursor can pull inside the gap, and press the left button and choose normal to this surface. And then the same, we can open the sketch. The sketch 1 will appear on the screen, and choose the square function, two-corner square function, and press the left button of the mouse. Keep pressing and pull the mouse move toward the right button, including the whole geometry on the screen, and release the left button of the mouse to create a square surface on between the boundary. And sure. Okay, then we have to remove the left part and leave the right part as our 6th component. How to do that? We choose this function and choose extend the surface, and to remove the material function. The same, he will automatically point to the right and give 10 millimeters for example. So this is direction 1. We have direction 2 as well. The direction 2 is this direction, but it open direction 2. The direction 1 cannot be closed. So we simply use direction 1 to change the direction from point to the right to the opposite direction, point to the left. How to do it? We can change this function. Right now, the original definition is to give the depth. We can simply choose to a point and pick a point. You put the cursor on one point, highlight the point, orange point, big circle, big point will appear on the screen. Then we say, okay, extend this area, this surface until this point first. The purpose is to change the arrow position to point to the right, change to point to the left. Okay, press down you can see the removing area big until to this point, and the arrow change from the right to the left. Okay, the direction is correct, but not include everything of the GA5. So we have to use another function to extend the removing area, including everything of GA5. How to do it? The same. We can choose the function to give the depth. To give the depth, the direction is correct. Keep remaining point to the left. The depth still the same. Be the original defined 10 millimeters. Then we give a big distance, suppose 300 millimeters. Press enter to see covered the whole GA5 area or not. This is covered, so we choose the correct depth. If we remove these parts, then we can leave the dark parts J6 on the screen. So okay, press this button. The system will remove the J5 automatically for us and leave J6 on screen. So after this, we can save PRT as well as IGS file. Choose file and save another new file, and the style is .prt, and the file name give FN6. So we save FN6.prt. Okay, then we save IGS file. The same, choose save another new file. The style, choose IGS.IGS. The file name FN6, the same, and save it. Then FN6.IGS will be saved. And right now he say yes, you choose the body, the chosen body, because we highlight here. Okay, we just remove it first and pick nothing. How to remove the highlight? Just simply put the cursor anywhere on the vacant position and press the left button. Choose nothing, then the highlight parts will be removed. Then we can save the IGS file right now by choosing save another new file. The style, give IGS.IGS. The file name give FN6 and save it. Okay. Now the last component, FN6 saved. Right now we are doing the tool. Suppose we still use the welding tool as before. So we have to put these points is what we said, the original point of TCP. We can press it to get the position 1341 Y0 Z1605 position. We choose defined, original defined, the tool of the welding on the origin of a Cartesian coordinate, and then use locate the tool to let it join to the origin of TCP points. So we leave the J6 on the screen. Okay, right now we need to use assembly picture, not this one. So we close it, simply by close the old file to clean the screen, and then choose a vacuum assembly file, close it, and sure, so nothing assembly on the screen. And then use insert component. Insert which one? Insert last one, FN6, and open it at its original location. And to see its location is correct or not, put a cursor on the edge, highlight, and press the left key of the button. 1341 0 Z equal to 1605. So this is correct. Then we arrange the tool of welding. How to do it? Simply insert component to give the original defined component at D and Unitech, and choose the CO2 welding tool as our memory tool, and open it at its original position. And what is the original position? The position locate the tool original defined, locate on the center, on the original point of a Cartesian coordinate. Then we have to later this point to combine with the original points of TCP points. How to locate this one to the right position? We have to remove the mark in front of our tool. How to do it? Simply by press the left button of the mouse and choose floating to remove the fixed, and then choose it to highlight the component and use move the component function. And choose from data SYZ to give the correct SYZ value to let this point move to this position. If we forget, simply go out and find the position first, then press OK. Remember 1341 1605. Simply select, simply choose move the component, and from data SYZ, and give X 1341 and Y remains 0 and Z 1605, and OK. Then the tool will move to the right position. Then the new TCP point will, according to our CMS CIPP, will change to this, the center of this point, to the tip of the tool. Then OK, we have to save PRT file and IGS file of the tool. Then we remove the GS6 first, choose it and press the delete key and choose yes to leave the tool only on the screen. Then we can save another file .prt style, then give the file name as FN tool. The folder, you have to choose the correct folder, the DFN FANUC 710, open it, D FANUC 700, and give the file name FN tool. fn tool. Okay, we save fn tool.prt first. Then, how to save IGS file? We remove the screen first, no saving, and then open and vacuum assembly file. Close it. Okay. Then vacuum assembly file opened. Then use insert component function to insert the fn tool at its original position. That means this one is TCP original to get the TCP point in here. So after this one, only the tool on the screen, then we can save the tool's IGS file. How to do it? Choose the file and choose save another new file and give a style as IGES.IGS and the file name give fn tool, and then we can save fn tool.IGS. Okay, after this from fn0 to fn6 including the tool fn tool, totally is 8 component IGS saved. Then we can translate this IGS file, 8 IGS component, by means of polytrans, change its style into .x file to prepare the S file before filling the CSV table of the scene of FANUC 710. When we leave SolidWorks and into polytrans, we started the translation started from the foundation. Use translate function, choose input 3D geometry. The style is the IGS. Choose this function v5.3 via Okino ASCII file, and the folder choose D FANUC 710. D FANUC 710. The foundation is fn0 IGS and open it. Okay. Yes. Start scene optimizer. Start. Yes. Okay. The foundation appeared on the screen. Everything is correct. Then we save the positive part of this component and then save the negative part of the component. How to save it? Translate, export 3D geometry, direct S file style. Now save the positive first. These 2 items not picked. Okay. The file folder correct. Then for the positive, we name it fn0. fn0 is the foundation. A means positive parts. We save fn0a.x first, and then save the negative parts by means of translate, export 3D geometry, direct S file style. The negative parts, we have to pick reverse orientation of all polygons and the normals, and pick flip polygon normals to let the normal direction to the opposite direction. So the positive and the negative for each surface, for each triangle surface, we combine the positive and negative as the whole components. Then we can reflect the lights from any direction. Thereafter, the component could be seen clearly. Okay, the negative parts we give fn0b.x and save it. So how to combine the positive and the negative? First of all, we have to use this recessing negative to clean the screen, and then use import 3D geometry direct file to import the positive of foundation from FANUC 710. The positive of foundation is fn0a.x and open it. Okay, yes, so fn0a on the screen. Then we import 3D geometry direct file to import the negative parts X file from the folder FANUC 710. The negative name is fn0b.x and open the O file. Okay, yes. Then fn0a and fn0b altogether appeared on the screen. Then we save the combination of positive and negative component by select export 3D geometry direct X file and give the positive direction only. Okay, and the file name remove the B, only fn0. Press enter. Then we can save fn0.x. The rest all the same. The procedure all the same. Then we can get the J1 fn1 x.x. We can get fn2.x, fn3.x, fn4.x, fn5.x, fn6.x, and the last two fn2.x. The totally 8 X file created inside the FANUC 710. Then we can copy this A X file, that is fn2.x, fn6.x until fn0.x, and copy this AX file into our CMS CAPP data area, that is CMS GAC data file folder position. After this 5X file into the CMS CAPP data area, then we can copy a Excel CSV file and change the name to the right name what we want, and use edit function to change all the data to the right data and check the results, the sync CSV file correct or not. So we commence to do that into the CMS GAC data, and we prepared already, so we choose fn start CSV. We just simply survey if everything inside is correct or not. So we give name fn means FANUC 710, new means new rule to define the limitation, and the RGB arrow for the TCP points. So we simply open it by press the left button twice. Okay, we check fn0, the base.x, give mesh 0, object 0, attached to itself 0. fn1, the j1.x, the give mesh 1, object 1, object 1 attached to object 0. The j2, fn2.x, give mesh 2, give the object name 2, object 2 attached to object 1. j3, fn3.x, give mesh 3, the object name 3, the object 3 attached to object 2. fn4.x give mesh 4, object 4, object 4 attached to object 3. fn5.x and give the mesh 5, the object name object 5, object 5 attached to object 4. Okay, the last one, fn6.x give the mesh name 6, object name 6, object 6 attached to object 5. The tool, fn2.x give the mesh name 7, object name 7, object 7 attached to object 6. So these x file attached to all be correctly defined. The rest, the next 6 is the limitation of J1 to J6. The last 3 is the RGB standard errors. The mesh named in sequence 9, 10, 11 until 16. The object name the same 9, 10, 11 until 16. For RGB error, we have to attach to the component 6 the same component as the tool, object 7 attached to 6. This is very important. Don't mix up. And the standard RGB translocated will give 99. Okay, then before we doing the virtual machine and the physical machine's definition, that means the driven axis of motion control car 1 until 6 axis, we have to make sure the last parameter is 2. 2 means mechanism 2. This is a standard 6-axis Modbus definition. Okay, we continue starting from the first axis 1. The first axis 1 driven the J1 fn1. We talked already, rotating around the positive z direction. The n1 0, n2 0, n3 1 is a rotating, rotate is rotating axis. So we say rotating around the z-axis, we leave z pivot to any value, but we have to make sure x pivot and the y pivot is 0, 0. How to make sure? We go back to the SolidWorks to insert the foundation fn0 at its original position, and to see the rotating center from the edge of the circle, putting the mouse on the edge of the circle. A highlight orange circle display appeared on the screen. We simply press the left button of the mouse, then the center 0, 0, 266 appeared at this position. We know rotating around the z-axis, we don't worry about the z pivot. Simply we make sure x, y is 0, 0. Let's go back to Excel. X pivot 0, y pivot 0. So the first axis correct defined. Then we go to the second driven axis. It is rotation axis J2, rotating around y-axis. So n1 0, n2 1, n3 0, 0 1 0, rotating around y positive direction. Then rotating around the y, we don't worry about the y pivot, leave the value to be anything. we have to make sure S pivot 150 and the Z pivot 565 is correct. Then we go back the SolidWorks to insert the one on top of the basement FN1 component and leave it its original position. The J2 is rotating from the circle. We can see the center, and to make sure X and Z is the correct as our CSV table, we press the left button to get the center down here. So 150, 565, 150, 565. So the second axis is correct. Then we go to the third axis. It is rotation component FN3 driven by third axis of the motion control car, rotating around the y-axis, y positive direction. So N1 0, N2 1, N3 1, N3 0. So we leave the y pivot value to be anything. We have to make sure the S pivot 150 and the Z pivot 1435 is correct. Then we go back to the SolidWorks to insert FN2 at its original position. From the circle here, we can see 150, 1535, 150, 1435, 1435. So it is correct. The third axis, okay. Then we go to fourth axis. It is a rotating axis around x-axis. So N1 1, N2 0, N3 0, 101 rotating direction. So we leave X pivot be anything. We have to make sure Y pivot be 0 and Z pivot be 1605. So go back to SolidWorks to insert FN7. Open it and put in its original position, and to see the center of this circle, and press the left button of the mouse. So Y0 Z 1506 1605, Y0 Z 1605. So the first axis of the motion control car, the parameter defines correct. Continue to the fifth axis of the motion control car, which is translate. Rotate is a two rotating axis, rotating around the y-axis. So N1 0, N2 1, N3 0. We have to make sure X pivot 1166 and Z pivot 1605. So go back to the SolidWorks to insert FN4 on its original position. We can pick the center up on here, or simply to open next component. Okay, we do this one first to see the center, how much. Press the left button. So we get 1166 1405, 1166 1605. So the fix correct. So the last one, the sixth axis of the motion control car, the component is FN6. It is a rotating axis as well. The last one we know, three of the pivot points is very important, although it's rotating around x-axis 101. Before we say if rotating around the 101, the x pivot point cannot be anything, but simply because we have the tool to define it, we have to give an accurate x pivot point, otherwise we will change the RGB arrow position. Okay, let's go back to the SolidWorks to see this 3 value is correct or not. Then we open the last one, insert the component FN6, the last one, and appeared at its original position. Okay, and find the center of the original TCP points and press the left button while the highlight circle appeared on the screen. So the center 1341.0.1605 to see the Excel the data is correct or not. 1341.0.1605. So the 6 axis is correct as well. The tool, the same, has to mark transrotate 3 and the SY pivot, Z pivot, S pivot 243.3, Y pivot 0, Z pivot minus 25, rotating around Y 30 degrees. So the tool is correct. The limitation, the transrotate for the first axis is 4. How to get 4? Is 1 plus 3 to get 4. Write 4 here. So from 4, 5, 6, 7 until 9 to define this 6 axis limitation. The positive right in this column, the negative of the rotation right down here. We get this data from the DM of FANUC 710 to fill in this area. Right now we remove this one and to check first. The last 3 RGB arrow we talked already. We have to write the attach tool to the tools attached to component 6 and transrotate. We have to write 99 as the new rule of the definition of the standard RGB arrows and leave the rest remain 0. So the Excel CSV file seems correct. Let me save it. Yes. Close it. Yes. And save the file name FN710 new and save it. Save. Yes. After saving, we can go back to our program to see the CSV file is correct or not. Simply use new to remove the geometry on the screen and use scene input function to input the data from D CMSGAC data file folder and to find the previous defined CSV file FN710 new. Open this file, which will display on the screen like this. Then we can see anything missing. It seems all correct. So X file including the tool RGB all correct. Then we can survey the attachment. The parent and the children relationship is correct or not by choose the teaching mode to check the join mode first, starting from J1. The right hand rule, the J1, the parent no move, the children all follow. So J1 correct. The J2, the parent 2 don't move, the rest all follow correct. The J3, the J4, and the J5 and J6. So the join mode all correct. Then we check the Cartesian mode. How to change into Cartesian mode? By putting the cursor on top of join and press the left button of the mouse. Then the system will change the join mode into Cartesian coordinate system. Then the x positive. What is x positive? X is R arrow, G is green arrow, and Z is blue arrow. So x positive, that means according to the direction of the arrow pointing direction, will move the TCP point along the direction. The system will use these points Cartesian coordinate translate back to see the TCP original position, simply because the tool has 6 transformation XYZ, RX, RY, RZ rotation. So from these points, after the reverse process to get the TCP position, and then use inverse process to get from J1 until J6 movements, then we display here the 3D acceleration. Dynamic join will follow in real time, and to see S minus direction is correct or not, and correct, and the Y positive correct, and the Y negative direction okay, and the Z positive go this way, and the Z negative go this way, and RX positive rotating around X. So these points and the red arrow no move, the thumb pointing the same direction as the arrow pointing direction, and the forefinger, curved finger, will turning the positive direction. So it will RX positive will turn this direction. Let's see it is correct or not. So the red arrow don't move, the rest turning according to the right hand rule. So how about the RX minus direction? It seems correct. Then we check RY positive, the same, correct. RY negative, okay. And then RZ positive. RZ positive means the sun point to the blue arrow, the same arrow direction. The rest the forefinger curved to show the turning direction for the positive. So RZ positive will turning. You can see it is correct, RZ positive. So how about RZ negative? It seems correct as well. So the Cartesian coordinate teaching operation is all correct. Now we check the robot setting, the choose function. After the choose function, a select 0 appeared on here. Then you can choose any axis by putting the cursor on top of any component. Choose how to choose by pressing the left key of the mouse button. As you press the button, you can see select 4. The J4 are selected. Now how to move the J4? Simply put the cursor any places on the screen and keep pressing the left button of the mouse and move the mouse to the right to turn J4 in positive direction. You see on the screen. If you keep pressing the left button and move the cursor to the left of the screen, then the J4 will turn the negative direction of J4. Okay, then we can put the cursor on top of select and press the left key once, then 4 becomes 5, and press twice, the 5 becomes 7, and press 3 times, select 10. So what is select 10? 7 is this 8, 9. So the select 10 is rotating around X positive in Cartesian mode, just Rx positive. So how to do it? At select mode, simply keep pressing the left button of the mouse and move the cursor to the right. You can see the red arrow now moving and the system turning according to the right hand rule, and use inverse process to calculate from J1 until J6. Also, the tool matches inverse process transformation as well. Let's move toward the left, then we will doing Rx minus. So it is correct. If we put the cursor on select and press the left button of the mouse once, the 10 will minus 1 become 9. If we press the left button twice, the 9 will become 7. We're doing the job the same as talking previous. Okay, before the end of the demonstrations, we use a practical the CAN system to show how this robot works. Go back to the menu. Choose the size function to give a square. The XYZ 300 is 310, and put the DSF file, translate the geometry on the center of 310 at the top of the raw material. And here is from the material to define the original of the Cartesian coordinate. That means these points. So from these points to see the position of the material is with 1 minus symbol difference. So here write x minus 800. That means from here to go x direction 800, and to go positive y 200, and go up z 300 to get the center of the raw material. Okay, let's see. Okay, so this is the location of the raw material, and before DSF input, we have to make sure DSF parameter is correct or not. The cutting speed set 100 millimeter per second, and the z-axis lift height remain 0 millimeter. Okay, then as in Cartesian coordinate system, we choose DSF input, give a file name beauty, and open the file. The CMS CAPP system will automatically give the toolpath instructions in data area. So harmony and draw the picture on top of the screen. So how many datas we can use head tail to choose the tail. The total is 3086, 3089 instructions of the toolpath of this beauty. Then we can enlarge the drawing and use water jet or welding, CO2 welding, to go along path to show the demonstrations, and automatically ending these demonstrations after the toolpath going to the end.
我是冬天里孤单的白玫瑰，就算天气黑，就算夜晚还在睡，就算你让我自己一个人喝醉，我不再心碎，也不会继续枯萎。我是冬天里绽放的白玫瑰，就算大雪飞，就算寒风刺骨吹，就算你。大雪在纷飞，寒风刺骨吹，那也比不上你给我的伤悲。我承受着最黑，要装作无所谓。我是冬天里可怜的白玫瑰，那么黑，人人不舍，也不应该让我一个人醉。寂寞的滋味，让我一个人体会。我是冬天里孤单的白玫瑰，就算大雪飞，就算寒风刺骨吹，就算你给我再痛再苦的伤悲，我不会落泪，也不会继续憔悴。我是冬天里虔诚的白玫瑰。夜晚那么黑，月亮我又睡。